Welcome to the Media and Connectors module of Network Plus for medical devices. Think of network media as the bloodstream of your digital hospital. Everything rides on it. In this session, we'll map the strengths and limits of copper, fiber, and wireless, plus the connectors that literally hold it all together. We'll keep the slides light and the notes practical. You'll learn how media choices affect speed, reliability, and safety, and especially in EMI heavy spaces like ORs and ICUs. We'll also cover where each option fits, how to avoid common mistakes, and what to test first when a link goes dark. By the end, you'll be able to pick the right medium for the job and speak confidently with both IT and biomed teams. Why does media matter so much in healthcare? Because every waveform, image, and order travels across these links. A 5-second delay in a PACS transfer can stall a radiologist. A dropped packet on a patient monitor might trigger a false alarm. Hospitals are noisy, electromagnetically and operationally. Choosing media that tolerate interference and deliver low latency directly supports patient safety. There's also security and compliance, segment clinical traffic, encrypt in transit, and log access. The trade-off is cost versus resilience. Copper is cheap, but shorter range and EMI sensitive. Fiber is fast and immune, but pricier to terminate. Wireless is flexible, yet needs careful design. Our job is to make those compromises explicit and intentional. When we say network media, we mean the channel that carries the signal, copper pairs, glass fiber, or radio waves. Each has a distinct profile. Copper is inexpensive and easy to work with, but limited to 100-meter channels and susceptible to noise. Fiber moves photons instead of electrons, shrugging off EMI and supporting huge bandwidth over long distances. Wireless adds mobility for telemetry and tablets, but it's shared spectrum and demands tight security. On top of that, PoE can power devices over copper, which is great for monitors, cameras, and access points. Always weigh speed, distance, and interference and costs. And don't forget environmental ratings, plenum spaces, cleaning chemicals, ingress protection, and antimicrobial jackets in clinical zones. Copper remains the workhorse for bedside and local links. Expect Cat5e, Cat6, or Cat6a with a hard 100-meter channel limit. In noisy locations near electrosurgical units or motor drives, spec shielded cabling and keep pathways away from power. PoE, PoE+, and 802.3 BT can power access points, cameras, and some patient monitors, reducing wall breaks and clutter. The upsides are cost and flexibility. The downsides are EMI vulnerability and distance constraints. Watch grounding and bonding, maintain bend radius, and avoid tight cable ties that deform the pairs. If you're troubleshooting, start with the basics. Check for damaged RJ45 tabs, missed punches, or exceeded length. A quick certified test can save hours of guesswork. Fiber is a hospital backbone. Because it carries light, it's immune to electromagnetic chaos in ORs and radiology. Use single mode OS2 for campus and long risers. Use multimode OM3, OM4, OM5 for short to medium length runs between MDF and IDFs. LC connectors dominate for density. SC still shows up in older panels. Cleanliness is everything. Contamination is the number one cause of fiber faults. Typical use cases include PACS and VNA storage, cross-site links, and 4K, 8K surgical video, where bandwidth and low latency are critical. Pull gently. Respect minimum bend radius and document polarity. If a fiber link drops, inspect and clean end faces before you swap the optics. You'll be surprised how often that's the fix. Wireless brings mobility, great for telemetry, tablets, workstation on wheels, and portable imaging viewers. But you have to design it like a utility. Start with surveys for coverage, capacity, and roaming. Use WPA3 Enterprise with 802.1x. Segment SSIDs by role and apply QoS so clinical traffic isn't competing with guest streaming. Expect interference from neighboring APs, building materials, and non-Wi-Fi devices. Channel planning and RF hygiene matter. Latency and packet loss can impact real-time monitoring, so plan redundancy and make sure critical apps degrade gracefully offline. Keep firmware updated and track device radios. Some older clients struggle on 6 GHz. Wireless is powerful, but it's not magic. Treat it as an engineered infrastructure. Connectors are small but consequential. On copper RJ45 is king. Watch for broken latches and poorly terminated keystones. On fiber, LC, SC, and ST are common. Confirm polarity, sitting, and cleanliness. Switches use pluggable out optics. SFP, SFP+, QSFP. So match the transceiver to the fiber type and distance. You'll also encounter coax connectors, BNC, SMA, in specific imaging and telemetry paths. In clinical environments, look for medical grade connectors with locking or keyed designs and proper strain relief. Label both ends, follow color conventions, and avoid mixing patch cord types. When a link is flaky, reset, inspect, and clean first. Then swap patch leads and optics methodically. Most mystery faults are simple mechanical issues. Let's map this to real life. In radiology, a fiber backbone holds MR and CT data to PACS VNA with minimal delay. In an ICU, copper with PoE ties patient monitors and cameras into the EMR and nurse station. In the OR, 4K surgical video often rides dedicated fiber, while device control uses copper. Hospital telemetry lives on carefully designed WLANs, with dedicated SSIDs, roaming tune for handoffs, and QoS for alarms. None of this works in isolation. Biomed and IT collaboration is essential for timely change control, risk assessment, and after-hours cutovers. If you see chronic dropouts, look for shared causes: dirty fiber, bent jumpers, overcrowded channels, or bad patch habits. A few habits go a long way. Label panels, drops, devices, and VLANs, so on-call teams aren't flying blind at 2 a.m. Respect bend radius and pull tension. Kinks and over-tight bundles hurt performance. Keep fiber clean and capped. Invest in a simple inspection scope. Separate data from power. Maintain tray fill limits. And avoid running copper parallel to high current lines. Standardize patch colors and lengths to reduce spaghetti. After changes, certify links and capture results in your documentation system. These aren't glamorous steps, but they prevent most outages. When something breaks, assume a physical cause first. It usually is. And prove the layer before escalating to software or servers. Where is this heading? Wi-Fi 6/6E is mainstream, and Wi-Fi 7 is appearing in labs, offering better efficiency and deterministic latency. 802.3 BT PoE supports higher power endpoints, shrinking wall adapters, fiber deep designs such optics closer to the edge, reducing copper length and EMI exposure. Some hospitals are piloting private 5G for predictable mobility in hard to cover areas. Through it all, the goals don't change: reliability, security, and observability. If this helped, subscribe and follow the rest of the series. Drop your questions below, and if you want the slide deck, the link is in the description. See you in the next session.